bridge of storm in the Bay Area. Okay, seriously, so you'll pick up your midterms and solutions after the quiz. I also sent an email or a Piazza note about makeups. So next 3 weeks, at least like one lecture a week will be a makeup. So take a look at that note. For example, you don't have a class this Wednesday, but there will be 2 on Friday. Okay, and then correspondingly, because I'm traveling next 3 weeks for like 1 day. Okay, so I wanted to just do a little bit of a recap on where we left off. It's been a while. Since like we actually had a lecture, and I wanted to do a recap of the 2-stage op-amp frequency response analysis and sort of this pole movement with compensation, and then we're going to go into some more details about it. But these are sort of the last 2 pages that we covered in the last lecture. So it was our 2-stage op-amp topology, where this, let me maybe just change the color so you can see, where we added this compensation capacitor and tried to see what is its relationship with the total lumped capacitances at this node and the output node, and how that determines the location of poles and zeros that we have. And actually, this sort of boiled down to this following. We could call it like a pie model, where you have a bunch of stuff lumped on one side and another, and then you have a bridge capacitor. We've covered that sort of from 2-stage op-amps previously, as well as even like in a CGD kind of impact on a single stage. You always get this kind of topology. And what we derived was that if you go and really kind of write out the nodal analysis, what you're going to get is that you not only have these 2 poles, but and kind of a classical DC gain, which is just stage 1, stage 2. GMs and R outs, but you also have this 0. Okay. And if you look at the expression for P1, one way to interpret it is that there is a C times 1 plus times the gain of the second stage. So that was this GM5 and whatever is the output resistance. And then C times that is really the Miller cap that is reflected back right here, right? So when we break the feedback of this Miller capacitance, what's lumped to C1 is essentially C times the gain of the second stage. And then that C really is then limited by the output resistance of the first stage, and that gives us the dominant pole, right? So that was, you could go about it via dominant pole analysis or by sort of open circuit time constant as well. Now pole 2, people remember this is sort of the formula that we derived from these types of topologies, where you have C and C1, C2 bridge across. And if you do the simplification that C is really increasing or very large compared to these other parasitics, you're getting something that is just GM5 over the C1 plus C2 parasitics at the input and the output of the second stage. So here and here. And then this is the P2 once C is very large. If you look at what P2 is when C equals 0, P2 was really just the C2 and then loaded by the output resistance, okay, R2. And GM5 is much bigger than the output resistance, the 1 over RO5, RO6, which is the output conductance. And therefore, this P2 prime really shifts way out compared to the previous pole with this C capacitor not being present. So if we're looking at this with and without this capacitor, the pole P2 really shifts by quite a lot. And that's what we essentially mentioned under pole splitting. So if you look at in this space of where poles and zeros are, P2 starts from here and then shifts out toward this P2 prime. And then P1 starts, with increase in C, starts shifting to a smaller magnitudes. And that's how we essentially do compensation, because we start breaking the gain or lowering the gain sooner, right, in order to hit wherever the P2 prime moves. Now, one of the artifacts was kind of bad about this pole splitting was that we sort of previously neglected when we only looked at poles. We said this effect was good, right? Because we're getting kind of the separation in poles. We're not only moving P1 to be lower, but we're also extending the P2. And we know that when we tie the feedback, really, if let's say at 45 degree margin, P2, that new location of P2 will be kind of our bandwidth of the amplifier, right? So that was all good. But the problem is that as P2 is going out, the zero, which is just GM5 over C, with C increasing, zero is actually starting to move in. Now, the bad thing about this zero moving in is that this is actually a right half plane zero. Right? Notice that there's no negative sign over here. And with that, this zero actually further ends up decreasing the phase margin. Okay, so it's sort of in phase, it acts just like a pole. Okay, but in magnitude, it's keeping your it's increasing your amplitude by 20 dB per decade. Okay, so what you have, and we can sort of sketch that in the next lecture. So we have this zero. Which is GM5 over C. We have the pole, let's say pole P1 is 1 over R1C times GM5 R2. And then here R1 is RO2 in parallel with RO4. And R2 is RO5 in parallel with RO6. So these are all first and second stage output resistances. And then we have that P2 will be just GM5 over C1 plus C2. Okay, so let's take a look at what happens with the Bode plot as this zero starts kicking in. Okay, so we'll have like a log. It will be angle of A. Again, we're going to start from something that is a DC gain. In this case, DC gain will be proportional to first stage transconductance times R1, which is the RO2 in parallel with RO4. So that's our DC output resistance. And then times GM5 times R2. Okay. And then we start breaking at P1. Okay, so let's maybe do this. So we start breaking at P1, and I'll push it down so P2 starts breaking over here. And so the phase starts going up until here. Here it's at 90, continues, and then it's another 90. Okay, so now depending on where that 0 is, meaning what's the relationship of C versus C1 plus C2, because C2 will be our C load. So if C load is big, then maybe P2 is happening before 0. If C2 is not that big, then as C increases, it may start, GM5 over C may start hitting kind of very close to P2, right? So we could have a situation where somewhere over here, we start breaking because 0 is over here. And then in this case, that would mean that we actually start breaking to pi or another 90 degrees down because of the right half plane 0. Okay. So notice that P2 over GM5 C1 plus C2, that's sort of the final destination of P2, right? As we're, yeah.
What if the 0 maybe go to 20 instead of 0? Does it start at negative 4?
Sorry, yes, you're right. Okay, good catch. So this is minus 20, minus 40, and this would kind of flatten it to minus 20. Okay, so kind of a little bit more worrisome than the slowdown in amplitude roll-off is actually the proximity of this increased phase roll-off. Because notice what's happening is that P2, the way we wrote it here, was GM5 over C1 plus C2. That's for like C being really super large. Okay, normally it would be C would be mixed in here. As a C over here and then C in the denominator, right? So as C is increasing, 0 is dropping much faster than the pole is actually increasing. Okay, so there may be a scenario where the two are very close, or 0 actually comes below the pole 2. If 0 is very close, notice that our target, for example, where we put our bandwidth, our crossing, at the final position of P2. So let's say that we start dropping our, let's call this position over here as 20 log 10 of 1 over f, right? So if you want this crossing to happen at P2, the shifted P2, then our shifted P1, or as P1 moves this way, let's say this is the new P1 location, it would have to be parallel, right? And let's say this is P2 prime. Previously, P2 was here, right? So P2 shifted this way, and P1 shifted that way. And then 0 started going from here and shifting this way as we start increasing the C. Right. So let's say we're targeting this, and we were assuming that just by looking at poles, if we do this, we would get here 45 degree. Right? If I put my crossing frequency, like my crossover of the A gain with 1 over f at pole 2 location, I would get 45 degrees, right? Because I've dropped 90 from the first pole and then another 45 to get to the second pole. So I would be good. 45 is a good. If I do it a little bit sooner, before that I may get 60, which is kind of a really nice phase margin. Okay? The problem is that if you're ignoring the 0 as it starts coming down, it starts getting this slope from 90 degree per decade to something that is like 180 degree per decade, right? If it's very close to pole 2, which means that this is now starting to roll off a lot faster. And that means if you're doing all the calculations so you park yourself at pole 2, you actually may be ending up with negative phase margin, just because 0 now started pushing in. Okay? So in order to kind of prevent that, we can start going and canceling that 0. But there's a few conditions I want to go through before that happens. So if you look at this, the first condition is that we want pole 2 to be greater than omega unity. Why is that? Well, omega unity is kind of the worst case that 1 over f that will happen at 1 over f. So when 1 over f is 1, right, that's our unity gain feedback, then the whole amplifier will have unity gain, right? And so what that means is that if we're parking our pole, our unity gain, which is in a closed loop, this would be our amplifier bandwidth, okay, up to this point, and then it will start rolling off. Okay, so in that case, because the amplifier would sort of itself look now like this, right, up to pole 2 and then go down. So because of that, if we push our P2 greater than this crossover, the worst possible crossover with unity gain, then we're ensuring that we're going to have at least a chance at taking a 45-degree phase margin. Right? So if you take a look at that, just in terms of the gain, so we said this was GM1, R1, GM5, R2, and then it starts going down. Let's call this now in the log scale. This is omega unity, right? So this will be the compensated pole. This is not the original P1, but it's the compensated one, which was R1cc, GM5, R2. So if we just look at this, up until omega unity, we're still plotting the amplifier itself, right? But the closed loop system would look something like this, and then start rolling off after the omega unity, right? If I'm tying in a unity gain feedback. So this would be kind of the bandwidth of my amplifier. In a closed loop, in an open loop, this would be the bandwidth of my amplifier. So the gain bandwidth is the DC gain times the pole. So it ends up being a ratio. We'll just make this C because that's what we used. Times the compensation C times GM5 and R2. So this was this A0 times pole 1, right? That was my gain bandwidth. So take a look at this. GM5 goes away, R2 goes away, R1 goes away. And this really ends up being GM1 over C. If we look at P2, P2 was GM5 over C1 plus C2. And we're going to say in a lot of situations, this really is approximately GM5 over C2, and C2 will be some C load. Okay? You'll see even in the lab and when you do the project, you're always driving a bigger cap out than it's your internal cap. So if you look at this, sort of one of the desires we want for a system that has a shot at a better than 45-degree phase margin is that we have this ratio that P2 is greater than omega unity, which means that GM5 over CL has to be greater than GM1 over C. Right. So from here, we sort of have that. So this is, oops. Okay, this is not good. Okay, so this was our P2. This was our omega unity. Right. And so you have that GM5 over GM1 times C over CL is greater than 1. So let's take a look at this condition a little bit more. To stabilize, this condition has to be true. We're pushing the pole after the, so we can make GM5 greater than GM1. And this basically means that I5 has to be greater than I1. So we should use W over L5 be greater than W over L1. The reason why we're doing it like this through sizes is that, remember, we want to have V overdrives the same. In both stages. Anybody remembers why we want that? Just intuitively. When did we worry about kind of KVL loops on V overdrive and VGS? Okay, swings, one thing, but here you would just get sort of a different swing range. It wouldn't enforce necessarily that all the V overdrives are the same. When did we worry about all the overdrives being the same? Yeah, so the systematic offset, we wanted to have the same overdrives in both so that the current mirrorings end up being the same, right? So second condition is that we also want this 0 to be greater than the unit gain frequency, right? We already said we're pushing the pole out, but a really bad thing is if the 0 starts coming before the pole, right? Because especially if it goes also before the unity gain frequency, because it not only starts lowering the magnitude roll-off, but also it starts accelerating the phase decrease, right? So we're getting this 90-degree phase shift from a 0 as well, right, half plane 0. So reminder, Z1 is GM5 over C. So here you have that GM5 over C is greater than GM1 over C, right? This is omega unity. So again, you get this condition that GM5 is greater than GM1. That's the same condition as we have on the pole. Now, whether it's a more severe condition depends on again on the load capacitance, right? Because the pole, second pole was kind of determined by also what the C load is, and this 0 really only depends on the compensation capacitance. Okay. So, as I said, you may have a situation where, depending on kind of your original roll-off, so let's see if this was P1, and then over here you get a 0, 1, or let's say in the normal situation you have P1, and then you have your P2, and then sometime later you essentially get, well, maybe we should do this. It's a bigger slope. And then we get another slope of -20. And this was a 0, 1. Now, these are before compensation. So with compensation, this pole would move this way. So let's say here. This pole would move this way. And this 0 would move this way. So you may end up with a situation where your new 0 is right here. Our new pole is somewhere here. And then the curve looks different. You start breaking from here. And then start going down till here. Then you flatten. And then you start breaking again by -20. Okay. However, your new phase then looks something like you go like this, then you go 90 down, and then you're going all the way to here. And then because of the 0, you go another 90 down. And then once you start approaching the pole, you get another 90 down. Okay. So because of this flattening, it may be that your 1/f is kind of somewhere over here. So by the time you cross, you have a negative phase margin. So this would be negative phase margin. Or if you're crossing somewhere earlier, right about where the 0 is, again, you don't have much of the phase margin just because of the 0, maybe 30, 40 degrees. Okay? So typically, what we do, instead of just enforcing this condition that Z1 is greater than omega u, we'll put it so that 0, 1 is kind of much bigger than omega u. Right? So this really means that GM5 over GM1 is much bigger than 1. Now, let's take a look at this a little bit. As we said here, we wanted to have W over L5 greater than W over L1. That was kind of representing GM5 greater than GM1. That was just for systematic offset. But this condition is actually much more problematic than just that. So it's in general the conflict between offset and stability. So let's take a look at offset. Right. We want to have L3 equals to L4, as well as L1 equals to L2. So L3 and L4 are the mirror or the active load, and L1 and L2 are input differential pair. Right? So both of these, you want them big. Remember, that was the way in which we minimized the delta I impact on the input referred offset. So when we looked at the random offset, the bigger the L's, sort of the smaller the input offset you would have, right? And so for that reason, you want them big to minimize delta VTH impact on VOS, right? Okay, so then we also have that, L3 is equal to L4 equals to L5 because of the systematic offset. Right. So what that means is that we also want L5 to be big. But now notice that in this condition over here, we want GM5 to actually be big. Right? So what that means is that we would want L5 to be small, so GM5 big. This is for stability. These are obviously two conflicting conditions, right? So you have to sort of see this trade-off, and depending on the specs that you get in your design, you would have to balance the two. So with these requirements, let's take a look how we can break some of these trade-offs by changing the topology, right? So this is all if we just have the C, right? But by adding some more elements, we may be able to counter this and effectively mitigate some of the trade-offs. So the strategy is to eliminate the right half plane zero. And so one way add a nulling resistor. So what we're going to do is I'm just going to sketch one stage, or like half circuit. Okay. And so instead of just adding a C between gate and drain, we're essentially going to add an R and then RC. So this is VO, this is VI. Well, if you take a look at this, we can redraw it kind of as a simple small signal model. And then I'm going to have R, C, and then another. This is VGS5. And this is V out. I'm ignoring here the the output transimpedance is RO2, RO1, and RO5, simply because they don't actually matter for this analysis. So if you take a look at this circuit, you can do quick KVL, KCL, and I won't do that right now, but I'll just write you kind of the final thing, that VO over this VI really ends up being minus GM1 over SC times 1 plus SCC, or in this case, we'll just do C. And then here, we not only have GM5, but we have R minus 1 over GM5. Okay, and so this piece over here, it's sort of this form, 1 minus S over 0, 1. Right. So our 0 is now modified. It's no longer just dependent on GM5 and C, but it also depends on this R. So you see that R is kind of canceling out the effect of 1 over GM5. So I'll write that 0 is now 1 over GM5 minus R times C. And now, if I pick the right R, I can go through a range of different scenarios, right? I can completely cancel that 0, or I can actually move it from right half plane into the left half plane as well. So if we just draw that diagram, the possible locations of the 0, so this is the S-plane. If R equals 0, we get what we had, which is GM5 over C. Then if R increases, if R is greater than, so if R is greater than 1 over GM5, then this piece becomes negative. So 0, 1 goes into left half plane. But before that point, 0 will be moving this way, right? As R goes from 0 and starts approaching 1 over GM5, this piece starts being smaller and smaller, which means that 0 increases, right? So as R increases, 0, 1 increases. And so it will be 0, 1 will be infinity for R equal 1 over GM5, right? And then we'll sort of come back from infinity into minus infinity and start going this way for R greater than 1 over GM5. Okay. Okay. So let's take a look at some of the key points for this. Okay. So if R is big, or big enough, we can push 0 into left half plane. And this will improve the phase margin, right? Because if 0 is in the left half plane, regardless if it's slowing down the roll-off in the gain, it will actually start boosting the phase, right? So instead of lowering it by 90 degrees, it will start boosting the phase, and that will help us fight whatever the poles are doing. Okay. Under B, let's look how R is implemented. Okay. We'll implement R as MOSFET in triode. So I'm going to have this, your capacitor here, and then here we'll put the and this will be V bias. This will be M5. Now, the question is, should I put this arrangement to be like this, or maybe like this? Any takers? Mm-hmm. Which side? The left or right?
The left.
Okay, so your left. Okay, left is. So you're saying this would be easier? What's the reason? Not just what's the bias voltage, but which arrangement is kind of more accurate, I would say, right? Because you put this transistor in and you bias it, you want it to emulate some R, right? For example, you want it to be greater than 1 over GM5 and turn it into left half plane. So as the circuit's working, is that always going to be the case, right? What if that transistor is not always with that resistance, right? So what affects the transistor's resistance? Right? I guess that in these two scenarios, that's what you should be looking at. In this one over here, we have a relatively small swing, and here is the output stage. Oops. So we have actually the largest swing we have in our circuit. Right? Here, it's, again, the same thing. Right? So over here, that voltage is not always hitting this node. So it's a little bit more shielded from the large swings at the output. Over here, it is directly hitting this node. So the resistance of this guy will vary a little bit more. Right? And because of that, it's kind of harder to control it to always be better than some condition, 1 over GM5 or whatever you set it to be. Right? So this is usually the preferred placement. Okay. So this is sort of the methodology to go about removing this right half plane 0. And you'll see in your lab 3 designs when you start playing with Miller compensation, if that's what you choose to do. And you will likely be forced to simply because of the kind of bandwidth requirements and the settling time that you'll have on the design, on the closed loop design. Then you'll have to toy around with these kinds of arrangements and make sure that you pick the right values for the R and in order to turn the 0 in what you need it to be, right? But there's no sort of like one recipe, depends on the specs. What's your phase margin, what's your settling time, et cetera. But this just gives you a feel of what the choice of that value for R will do to the circuit, right? It will either make it left half plane 0, get it to be completely eliminated from the picture by going to infinity, or sitting right around your second pole. Okay. There is one other condition that is actually also very important. So far we've been talking about kind of what the system does on a small signal excitation. Right? So what that means is that if I have a small signal input, we just talked previously about, okay, what if that input is sinusoidal, right? At some frequency, it will be amplified by, if this is sine omega A1, AI sine omega t, this will be A out sine omega t, or omega 1. Or it will be some smaller frequency, some smaller amplitude at a bigger frequency, right? So the ratio of these A0 and 0 prime will be sort of depending on our frequency response of the amplifier, right? If I start rolling off, then obviously A0 is going to be smaller. A0 prime will be smaller than A0. But if I put in a sign I'm getting a sign out. Okay, so that means it's a linear time invariant system. Okay, so that was the Bode plot or the frequency response domain view. You could also view it as kind of what happens in time domain if I put a small step response, right? So at some time t0. So this is input. What would you expect to see at the output? You put this little step at the input of your amplifier. What do you expect to see at the output? Okay, so at what point in time? Ah, okay, there's something like slew rate, okay. But at what point in time do you get the step? Can you get it before T0? No. You would be rich if you could do that. Stinking rich. Yeah. All the nano traders would really love you. Okay. So T0, of course, you can't. But so sometime after, it would start recognizing the input. And then ideally, you would want it to go just to a higher amplitude, right? So if this is AI, this will be AO greater than AI. In fact, AO will be just equal to AI times DC gain of the amplifier, right? But in reality, what does it do? It doesn't immediately jump to to that step, or not even in that perfect shape. What does it do? Okay. Assume a scenario. Like, okay, if it's overdamped. Yeah, like a single pole, for example, or two pole overdamped, it will sort of be sort of a dominant exponential that gets it to the goal. And as you start kind of critically damping it and underdamping it, it will become sort of faster to respond, but with a little bit of peaking. Okay, and sort of by tuning in the pole 1 to pole 2, and in fact this will depend also on your phase margin. You'll have a different scenario here, different amount of peaking where you want it. But this is all small signal stuff, right? If I now go and apply a bigger input, up to a certain point, everything will scale, and this response will be identical, just bigger, right? But at some point, it will actually cease to follow, okay? And what will happen is I put something like this, bigger in, and what I'll get at the output is something that looks just like this. And then it reaches the value. And there will be sort of a fixed slope over here that we call slew rate. The amplifier is just going to start behaving as an integrator, essentially. And the reason for that is, and I'll just sketch it here real quick, and then we can pick up a little bit in the next lecture. Is that we can taking a look at kind of the input stage of our amplifier, and now I'm just going to draw it a little bit differently, but I mean, it doesn't really matter. You're used to doing it both in P and N version. I'm drawing here just the model, the essential kind of thing. So these will be our input pair transistors, M1, M2. These are the mirror transistors, and then this is our first stage. This is our second stage. We had M5 and M6 here, right? And then we had around the second stage, we had this compensation capacitance C. That's essentially our op-amp model. So in the first case, we have small signal. We have that, for VID, let's say VID equals 0, right? We're dividing the current between these two. But and then any small fluctuations will really just translate into the gain. But in large signal, if VID is very large, much bigger than 0, what we have, for example, is that in this case, if this is plus minus, M2 will turn off. Okay. So this one will be off. Then all this current I flows this way and gets mirrored in here as I. Then you sort of, it doesn't really matter what VID is anymore. You've already shifted all the current to flow this way, and that current is capital I. It sort of cuts out the input from the output. So your dV out, this is VO, or dVO over dt is just I over C. If VID is smaller than 0, then M1, 3, and 4 are off, and then you're providing the current I from here, and that goes this way as well. So now you have dVO over dt is equal to minus I over C. So notice you do react to something, right? You sort of react to the sign of VID, right? So it's kind of moving you in the right direction, but the shape in which you're approaching that target magnitude is really independent of the small signal dynamics, of the linear system dynamics. And so this quantity over here we call slew rate. And if you take a look at the slew rate, to increase the slew rate, which is what you want for kind of faster response, you have to increase I and drop C. Now, again, this C is what we use we add C in order to compensate the whole amplifier, right? So here you see again kind of a problem. Lowering C, yes, you respond faster, but your amplifier is going to start being less stable. Right? So then you have some fundamental trade-off there. What you want is, so in this case, if I was just doing it through this reduces phase margin, right? Phase margin. So I would want to do it in such a way that I increase the slew rate, but I don't compromise my stability. So let's take a look